Guys, in this video we're going to discuss very briefly the concepts of domain and range, which are two very large concepts in math and are explored in greater detail typically with other things, but this is just kind of a quick intro to what they are. Okay, so I'm going to start by having you direct your attention up here. But what I've done is I've written down kind of an operational definition of what these two values are. Now, starting with the fact we call domain. You know, this is going to show up when we look at these things being these relations, these functions being represented graphically. But when you think of domain, you know, you kind of think of all the places that maybe one could wander or where one dwells. But domain, we say, is the set of all input, okay, which we typically associate with x values. Those are what we plug into functions. But the set of all input values for which a function is defined, okay, at least in a real number sense. And so what I'll do here is I'll kind of bring up two instances in which you would have x values for which your function would be undefined. I'm going to scribble them in here, but when you have division by zero, okay, division by zero, when you divide by zero, typically, you know, well, not typically, always, but you find that you end up with something that we say is undefined. So naturally, we would say if the domain is the set of all input values or x values for which a function is defined, if we were to run across an x value such that when we plug it in to a function, it doesn't spit out a y because it causes you to divide by zero because your function's undefined there. We say that x value or x values would not be included in the domain. Okay? And then the other instance would be, and I'm going to bring this up, is when you produce imaginary numbers. And if everybody remembers from algebra class, imaginary numbers occur when you try to take an even root, so like the square root or the fourth root or the sixth root, of something that happens to be negative. Okay? So we're going to look at those two instances over here, you know, actually here and here respectively. So I bet you just can't wait. And we'll talk about the range. Okay, so the range we say is no more than the set of all values that a relation or function maps onto, or y values. So this would necessarily be all of the y values that, say, an input would go to. And, you know, it may be the case that, for example, maybe I take all of the integers in the world and the relation between the integers I have and the other set is that I double all the integers. So now I've, you know, maybe illustrated a relation or a function between all the integers mapping onto all of the even integers. If they were to necessarily double and map onto the even integers, then all of the odds would not be mapped onto. And that's not a bad thing. It's just that they would not be included in the range. Okay, so let's talk about a few different representations of this. You know, we have this notation, okay, with ordered pairs, or we can look at them algebraically. We're also going to look at these graphically over here on the right. Okay, so let's start with this kind of roster notation here, A and B. But we say, okay, so we have some function here, f, okay, and what it's doing is it's mapping x values or input values onto y values. And what we're concerned with finding are the domain and the range, okay? So if these definitions hold up here, and they do, we say the domain was the set of all input values for which a function was defined, okay? So I'm already looking at all of these. These are our input values, but we'd simply say the domain then, okay? Each one of these input values mapped onto an output value. So they were not a value for which when we plugged it in we got something that was undefined, okay? So we say all of these input values necessarily would be included in the domain. We say -4, we say 1, 3, and 8. Those are the values that are included in our domain. And our range, the set of values that were mapped onto, simply were all the y values that actually got used. And in this instance, this is a very trivial example, but 2, -6, and 3 were all mapped onto. So we say these respectively are domain and range because these were all the input values that caused the function to be defined, and these were all the y values or output values that got mapped onto. Okay, same kind of thing goes up here when we look at letter B. We look at the input values for which the function was defined, and if any input value is going to an output value, we necessarily say then the function must have been defined for that given x. So again, this is kind of just a different looking example than letter A here, but we say, okay, so the domain includes the input values 0, 2, and -3. Those actually mapped onto output values. And the range in this instance would actually include the values that got mapped onto. So 1 got mapped onto by 0, 6 actually got mapped onto by 2, and 8 got mapped onto by -3. So it's really kind of an exploration of which x values worked, okay, and which y values got used. All right. So now moving on to letters C and D. You're going to notice that I've defined a couple of functions here, function G and function H. If this is really messing with you, you have permission to write y equals instead. They tend, well, they mean the same thing, but let's take a look at this, okay? Now, if, the definition here of this function is this, then we say we're not just going to be plugging in individual x values. We're going to be plugging in pretty much all real numbers into this function for this x value right here. What we're really concerned with domain, however, is which x values actually go into the function and spit out a y value that is not undefined, okay? Or imaginary. So we look at this one here and we say, okay, you'll notice that automatically we notice that there's an x in the denominator. And remember, we said the two things we want to be wary of are there any x values that would cause me either A, to divide by 0, or B, to cause this function to obtain an imaginary value, a non-real number value, okay? So I'm looking at this, and you notice that there's an x in the denominator. I'm going to give you a suggestion here. Whenever you see a function like this and you're trying to determine domain, the number one thing we don't want down here is we do not want this to be equal to 0, okay? We don't want this to be equal to 0. If it were equal to 0, then we'd have something undefined. So really the question now becomes, what are all the x values that when I put them in right here for x, it causes this function to be undefined? So the rule of thumb is this. When searching for the domain of a rational function, we say a ratio or a quotient, and there are x's in the basement, what we'll do is we'll take the entire denominator and we'll set it equal to 0. So in this case, we'll set x plus 5, which is in the denominator, equal to 0. And the reason why is because what we can do now is just simply solve for x. Once we do this, we find that x is equal to -5. Now, this is not a solution. This is not anything, other than an x value that we know would cause the denominator to be 0. Okay? And if what we're doing is trying to find the set of all x values in the domain, those are the x values that don't cause the function to be undefined, then we're going to write this kind of differently this time. We say the domain, okay? The domain would include all x values over these intervals. So we say from -infinity all the way up to, but not including -5, okay? So you're going to notice here that I wrote a parenthesis on both ends of this. It is the case that sometimes I may write from, say, 1 to 2 and write brackets. And this doesn't apply to this, what we're looking at right now. But if I include brackets, it means from 1 to 2, but also including the values of 1 and 2. And if you see an open parenthesis, what that means is everything from -infinity up to, in this case, say -5, but not including -5 itself. It does not include -5, okay? The domain, you have to realize though, would include all other x values from -5 all the way out to infinity. We could plug every x value in any of these intervals. It's just that we cannot include 5 itself. So we put these open parentheses here to denote that it's excluding 5, -5. It means up to but not including -5, okay? And as far as range goes, I'm going to leave that one out of this one because we would necessarily have to graph this function to determine what the range would be. Okay, let's move on to h of x. Now domain, okay, again, domain, recall, is the set of all x values that cause my function to be defined. And another way to say that is the set of all x values for which my function is not undefined or not imaginary. So recall that imaginary values actually tend to occur when you are trying to take an even root of a negative thing. So I don't want you to be tossed off by this negative right here. The question happens to be that, we notice we have a radical here and an x inside this even indexed radical. This is the second root of all of this. But the question is, so what would cause what's in here to be negative? So the rule of thumb is when you're dealing with an even indexed radical with x's on the inside, let's take everything on the inside and say, so what if it were negative? And the way we'll write that is this. 4 minus x squared, we'll set it less than 0. Okay? What we're concerned with are, what are all the x values that would cause this in here to be less than 0? So now solving for x, we say we'll subtract 4 from both sides of this. We'll treat it just like an equation. We end up with -x squared is less than -4. So now I use this example kind of on purpose with intent here because it kind of reviews algebra. But what we're going to do now is we're going to divide both sides by -1. And when you're dealing with an inequality, anytime you divide or multiply both sides by a negative, okay, we have to flip this sign right here. So now this is going to imply that positive x squared is now greater than positive 4. So the final thing we need to do here is this here. We're going to say square root of both sides. So we say x is greater than 2. Okay, and we can simply check this by trying to plug 2 back into this equation. If we plugged in 2 into this equation right here, notice that 2 squared is 4 and 4 minus 4 is 0. We could also plug in negative 2. If we plugged in negative 2, that'd be negative 2 squared is 4 and 4 minus 4 is 0. So the square root of 0 is 0, but we're totally cool with having a 0 in here. What we don't want to have, okay, is anything that would exceed this little set of values here. So what we'll say the domain is, we say is all x values from negative 2 up to positive 2 and including both of them. If we were to plug those exact values in or anything in between these, we're going to get 4 minus something smaller than 4 or equal to 4, and everything in here will maintain its positivity. But if you say we're to plug in negative 2.1 or positive 2.1, you would have 4 minus something greater than 4, which would cause this to be undefined. So all this does is say, hey, all the x values inside this little interval here, those are the ones for which your function are defined. Okay? Now the last two we'll look at here real quick are e and f. And the nice thing about this graphically is we can just kind of look at this, but notice I want to look at the domain of this. We said it was the set of all x values for which it spit out a y, or which your function is defined. So I would challenge you to look at this function and say, were there any x values that when you plugged them in, it did not actually go to a y value? And we could do this forever and ever. You know, we say this x value went to there, and this x value went to there, and this x value in there, and there, and there, and there. In other words, were there any spots from left to right that our pencil ever had to be picked up when we made this? And the answer to that question is simply no. Okay, so the domain of this would be all x values from negative infinity to infinity, because when we plugged in all these x values, we got a y to spit back out. Now in this instance, we said it's easy to interpret range, easier, when you have a graph. So range is kind of like saying, so what were all the y values that you actually plotted? And you're going to notice here that if I highlight this right here, this is a y value of 1, and it equaled 1 there, so a closed dot. We say we used all the y values from this positive 1 on up. We had a y value of 2 here, a y value of 3, 4, 5, and up and up and up and up, and this is going to go up forever and ever. But notice we didn't use any y values below this positive 1. So we'll say the range started at positive 1 and proceeded on upward toward but not including infinity, positive infinity, okay? So the range is kind of like saying domain, you know, from left to right, were there any spots we picked our pencil up? Well, from bottom to top, were there any spots that we never had our pencil down? And the answer to that is yeah, we didn't have our pencil down anywhere down here. It was all above 1 and including 1. So let's take one last look at this last example, f here. We say domain and range. We're going to keep using this interval notation. But you notice domain, now from left to right, we're tracing along this function, and it gets to an x value of negative 1, and you notice that I've got an open dot here. What that means is we didn't actually include that x value of negative 1, but we did everything up to and not including it, okay? And then we start up here again at positive 1, not including it, but everything kind of approaching 1, and then on to the right. So for this little gap right here, there were x values from negative 1 to 1 we did not even use. So we say if the domain is the set of all x values that caused my function to be defined, that is, actually went to a y value, then we can't include these in the domain, those x values. So we say the domain were all x values starting out at negative infinity and getting really close to negative 1, but not including it. So we'll put an open parenthesis here. And then it takes a break, and then it starts up again at positive 1 and proceeds on out to infinity. Okay. And as far as range goes, we say, okay, so which y values were used? Were there any spots from bottom to top of this graph? If we took our eyeballs and went from way down at negative infinity all the way up to positive infinity, were there any y values we didn't use? And again, you'll notice that both of these, this was the lowest height of our graph, a height of 0. But since these were open dots, it didn't actually include a height of 0. So the range of this function would be considered, it started at a height of 0, but not including 0. Okay, started there, everything up to 0, but not including it, and then proceeded to go on up and up and up and up and up forever and ever to positive infinity, but not including it. So this is just kind of a short little explanation of what domain and range are.